So we have a busy day, and we're going to do several things. First, I'm going to review our cited derivatives and our points of non-differentiability. And then along with that, I'll take a couple of homework questions about the cited derivatives and points of non-differentiability, just to make sure that we're all on the same page with those. In particular, I think numbers 5 and 7 would be good to look at. We'll also look at number 8, which was not in your homework, but is a good problem. Then, related to that, we're going to talk about your test tomorrow and what you need to know for that test. And then, if we have time, but I doubt we have time, then we'll talk about our lesson that I wanted to get to, which examines a little bit more what happens when f is discontinuous at x equals c. And I've actually already done a video on that. It's about a 9-minute video. So I'm anticipating that we will not have time for it in class. But if we do have a little bit of time, then I'll talk very briefly about that concept. But I recommend that you watch the video, which I've already posted out to admit. So really, these are our 3 goals with an optional goal, bonus material, if we get there. So, how do I pronounce this? F prime from the right. At C, exactly so. And how do we compute it?
Limit as C goes to, as x goes to C,
Just one small thing missing?
to the right C.
Yeah, only from the right, exactly so. And from the left?
Limit as goes to C from the
All that muttering was taking place because it's the same thing, but we're approaching now from the left. And overall, this is the derivative at C, so that we can observe that the derivative here can exist if and only if the derivatives from left and right are both the same. And so that was our two-sided derivative theorem, the two-sided theorem for derivatives. Which is that f prime of C is equal to some value d, if and only if f prime on the right is equal to d, and f prime on the left is also equal to d. So those were our sided derivatives, the left side here and the right side up here. Okay. Now we used these sided derivatives in a couple of different ways. First of all, we used these sided derivatives to find the derivatives of piecewise defined functions at their joints. Because if I have a piecewise defined function, such as f of x is equal to, oh, I don't know, x squared minus 3 for x is greater than or equal to 1, and x plus 2 for x is less than 1, something like this, then for x is greater than 1, f is a polynomial, and I can use derivative rules on it. And for x is less than 1, x is a polynomial, I can use derivative rules on it. But right at x equals 1, where my two pieces come together, or don't come together in this particular case, then my function is not a polynomial, because for x's in the neighborhood of 1, my function will have one definition on the left side of 1 and a different definition on the right side of 1. And so therefore, at the joint, we must compute derivatives from left and right. separately. The joint x equals 6. We must compute derivatives from left and right separately. Does that make sense to everybody? Yes, sir. At the joint, at the point where my two different pieces join up.
So you don't worry about piecewise function.
What do you mean you don't worry about them?
Piecewise function is important.
Yes, piecewise functions at joints. That's exactly it. So I'm saying in the case of piecewise functions, this is one major use of our cited derivatives, which is to compute the derivative at the joint. It's necessary for us to use cited derivatives to do that. Does that make sense? Okay. Now, a second major use of the cited derivatives was to analyze points of non-differentiability. Points of non-differentiability. And we said there were really 4 categories of non-differentiability that we considered. The first was discontinuities. If f of x is discontinuous at x equals c, then f prime of c does not exist. Yes?
Can you explain differentiability, or what it is? Okay.
The differentiability is another word for saying the function has a derivative. So if f is differentiable at x equals c, f prime of c is some number b. And so this would apply to any type of discontinuity. What are our 3 major types of discontinuities we've talked about? Vertical asymptotes, jump, and points of removable discontinuities. Exactly so. But then there are 3 different circumstances where a function could be continuous, and yet f prime of c will not exist. And the first one was a corner, where f prime of c from the left and f prime of c from the right are different values. And the classic example that we've used for that was the absolute value of x. And right at x equals 0, f prime of c from the left was what value? -1. And f prime of c from the right was +1. And just the fact that I have 2 different numbers for f prime of 0 from the left and from the right tells me that my function will have a sharp corner, because it means that my function has one rate of change coming in from the left, but a different rate of change coming in from the right, and it must therefore sharply go off in a different direction. That's it. So that was our corner. Then we had vertical tangents. And we made certain that these are different from vertical asymptotes. Vertical asymptotes are points of non-discontinuity. Vertical tangents are going to be places where the curve goes straight up. Or where the curve goes straight down. And our example function for this was f of x equals x to the 1/3. And you look at the graph of f of x, you can see that right at x equals 0, my curve goes vertical. So it has a vertical tangent. And on either side of 0, you can see that my curve has positive slope, so that as we get towards 0, my tangent line has infinite slope. Now, just looking at a graph, it can be hard to tell, because I can look at a graph and say that looks like it goes straight up, but I'm not really sure. And so ultimately, to know that you have a vertical tangent, you have to actually do the limit definition or the derivative to see that that derivative really does go to infinity and not just like 10 or something. Does that make sense to everybody? Okay. So that's vertical tangents. Now, related to the vertical tangents were our last and strangest type, and that was a cusp, where f prime of c from the right, excuse me, from the left, is negative infinity, but f prime of c from the right is positive infinity, or the other way around. Just like that. And our classic example function here was the bird curve of x equals x to the 2/3, in which, from the left, my curve goes vertical in a negative direction, and from the right, my curve goes vertical from a positive direction. And notice that in all three cases, corner, vertical tangent, and cusp, the function is continuous at x equals 0, but it is not differentiable at x equals 0. Yes, sir.
Or vertical tangent.
Uh-huh.
The derivative from the left and the right, there goes a has to something.
You mean derivatives from left and right? Yes. Derivatives from left and right will both be the same sign of infinity here, whereas they are opposite signs of infinity here. Yes. Good. Any questions about the material? Now let's take a look at the homework questions you had last night. And I want to focus on numbers 5 and 7. I might have a little time for you to consider others. And I also want to look at number 8. In number 5, we are given a graph. We are asked to identify all of the points where f is differentiable, where f is not continuous, continuous but not differentiable, and then for part C, neither continuous nor differentiable. So we're looking for these three things. Notice that a fourth possible option, theoretically possible option, differentiable but not continuous, does not appear here because that is impossible. It is not possible for a function to be differentiable but not continuous. That was our first type of non-differentiability, right? So, now we take a look at number 5. And number 5 is a linear function that looks like this. And so we're going to look for, first of all, points of discontinuity. Do you see any points of discontinuity on the graph? So that means that we're going to have no points where f is not continuous and not differentiable, or you could say that the set is the empty set. Now, we look for any points of non-differentiability, corners, vertical tangents, cusps. Do you see any? Neither do I. No points there either. And everything that's left over are going to be all the points where f is continuous and differentiable, and that is the entire domain from -3 to 2. And so we're done. One other way to look for this is to look for places where f is smooth. Mathematicians use the word smooth to describe a curve that is differentiable. And sometimes they'll make it an even stronger requirement that maybe the second derivative exists, or the third derivative exists, or the fourth, so on and so forth. So, and that gives them whatever degree of smoothness they need. For our purposes, if f prime exists, we'll say that f is smooth. And so that makes it easy to look at. I look at this curve and I see that it's smooth. It doesn't have any sharp corners or cusps, any places where there's a problem. Good so far? Now number 7 is more interesting because in number 7 we have a graph that looks like this. -3 to +3. And again, we're going to look for differentiable, non-continuous, excuse me, continuous but not differentiable. And neither continuous nor differentiable. Okay? So I'm going to start with discontinuities. Do you see any points of discontinuity? Where? Yep. So in part C, we identify x equals 0 as a place where f is neither continuous nor differentiable. Notice I'm really answering these questions in reverse order because the points of discontinuity are the easiest to see. Then, working backwards in part B, do you see any places where f is continuous but it has corner vertical tangent cusp? I don't either. So we're going to have no places where f is continuous but not differentiable. And that leaves us with all the other places where f is a smooth curve. And that's going to be from -3 to 0, together with 0 to 3. Yes? Yes, in fact, number 8 has a really good illustration of that, and that's what I'm going to do next.
For 8, can you do like -3 to 0 plus 0?
Yes, you can do that. You would express that like this. Set of all x like that. Actually, if you're feeling in a real hurry, you'll see this in the literature a lot. -3 to 3, take away the set consisting of the element 0. So that's acceptable notation as well. Number 8 is really interesting because we have a curve as this, and this right here. And so now the question is asked, the same 3 questions are asked. Where differentiable? And of course, if differentiable, automatically continuous. And where continuous but not differentiable. And again, it makes sense to me to work backwards. So let's start with C. Do you see any points of discontinuity? 0? And 2. Exactly. So x equals 0 and 2 are 2 points where the function has, what type of discontinuity do we have at x equals 0? Jump. And at 2? Point. Very good. And what you guys have done is trained your eyes to see those types of discontinuity, and the same thing happens with points of non-differentiability. You train your eyes to see it. Do you see any places on the graph where f is continuous but it's not differentiable? And what type of non-differentiability do we have there? And sure enough, as per the definition, the slope here is roughly -3, and the slope here is roughly +3. Yes?
You can't prove the quiz.
Correct. The graph, the directions just said at what domain points does the function appear to be? And there it is. If I knew that these were two straight line segments, then I would know for sure. And on a test or a quiz, I will make every effort to ask questions in which either I tell you you can use your eyes to estimate that, or I tell you enough information so that you can be sure. Now, what about points where f is continuous and differentiable?
I can say
And how am I going to join that? What sign do I use here? Yeah. Union sign. Pronounced union. We're going to include -3 and 3. Notice at the endpoints of the domain right here, the only derivative that makes sense is the derivative from the right. That's the value of the derivative right there. And the only derivative that makes sense right here is the derivative from the left. That's the value of the derivative right there. So on these domains that include endpoints, we take the value of the derivative to be the value that you get from the appropriate side. Okay? Jennifer, did that answer your question? Good.
Can you do number 11, Charlie's?
Yeah. Number 11, function fails to be differentiable at x equals 0. Tell what the problem is. Okay. Now, inverse tangent is a fairly obscure function for you guys. Later on, we're going to get really familiar with these. So I probably would have looked at a graph. And when you look at a graph of inverse tangent, which looks like this, with horizontal asymptotes y equals -pi/2 and y equals +pi/2, what do you see about the value of inverse tangent at x equals 0? It's 0, which means that the limit as x goes to 0 of inverse tangent, which is clearly a continuous function, has that same value. And therefore, when I consider our function y equals inverse tangent for x not 0 and 1 when x equals 0, it's really clear that my function's limit is a different value than my function's value. In other words, I have a discontinuity, specifically a point discontinuity. So the problem with number 11 is that this function is just not continuous. Yes, sir? And so we'd say it like this. The limit as x goes to 0 of y, 0 of y, and 0 of x. Jason? Repeat the question. The answer? Yeah. Well, really here, what's in the box? The reason our function fails to be differentiable is that our function fails to be continuous at x equals 0. And I can demonstrate that by comparing the limit to the function value and saying, hey, look, they're different. So our y actually looks like, pi/2 is here, y is right there.
The one. That is x equals 0.
Yes, right, y is 0 is 1. Yep. Okay. We actually have enough time for me to talk about 13 as well. we're told that y fails to be differentiable at x equals 0, and they wonder why. So I do a quick sketch. And when I do a quick sketch on my calculator, something interesting pops up, and that is that my function looks like this, and then it looks like, actually it looks like this, there we go, and then it looks like this. So looking at the function, does it appear to be continuous at x equals 0? Yes, it appears to be continuous, and I can check really fast mentally that from the left and from the right, I'm going to get 2 for both of those limits, and y of 0 will also be 2. So just mentally, I can see that I don't have a discontinuity problem. So we eliminate that from our results. Notice I'm checking continuity first, just like I did on graphs. Then, to diagnose all of my other types of non-differentiability, I use decided derivatives, exactly. So I would compute f prime for y prime at 0 from the left, as the limit as x goes to 0 from the left, f of x minus f of 0. Now my 2's cancel, which is nice. And I look at this limit, and it's got the form of 0 over 0. Not really sure what to do with that fact, but it does occur to me, one way I can handle this is to split up. And then I think to myself, so what is another way to think of the square root of x squared? No. Absolute value of x. Yep, exactly. And so now, as x goes to 0 from the left, x over x is the same as x over x is the same as 1. And absolute value of x over x will go to negative 1 as x goes to 0, so that I get 0 for my derivative from the left. And that makes sense taking a look at the graph of my function. But now y prime from the right is going to be the limit as x goes to 0 from the right. And here I can borrow the work that I did from the previous page, right? And so this limit is going to be 1 plus now 1, which gives me 2. How do I interpret these results? Derivative from the left was 0, derivative from the right was 2, therefore, corner. Exactly. And so we would write our result as corner because y prime left at 0 is 0. What's that? Yeah.
So this kind of question, we need to check continuity.
I would check continuity first because it's easy. And it helps to eliminate the one possibility. And then I can get into my decided derivatives to check the other 3. If I reverse that process, then my decided derivatives can be ugly. One of them will end up being infinite if my function is not continuous, or maybe both of them being infinite. And it's just not a great way to go. So check continuity first. Do that on the graph, do that analytically. Okay. Sure. There you go. You got a test coming up tomorrow. So what do you need to know for your test? Yeah.
It's like
You what?
35.
Give us a second.
Relative roots.
Yeah, good point. That's right. So we can work either backwards or forwards. If we work forwards, it looks like this. First of all, you need to know your two limit definitions. Let's have those. F prime of x equals. Okay. So here, let me get you started.
Oh, limit of x goes
And, limit as h goes to 0 of
f of x plus h. F of x.
Exactly. This evaluates f prime of x in general. Yeah. Meanwhile, if I want f prime specifically at point C, then that is equal to
F of x. Oh, limit x.
you go.
F of x minus f of c. Or x minus c.
And both of these definitions have the same picture, but they label the information differently. So, what we're talking about is a function like so, and in the first case, I'm going to a point x to find the slope of the tangent line right here, and I go out to a point x plus h, and that gives me two y values, f of x plus h, and f of x, and the slope of the line connecting these 2 points is going to be delta y over delta x, which is f of x plus h minus f of x in the top, divided by x plus h minus x in the bottom. That gives me h. That's the average rate of change of y with respect to x. To make it instantaneous, we let delta x go to 0, which gives me the slope of the tangent line. So notice secant line, slope, difference quotient. Tangent line slope, limit of the difference quotient. Yes?
Where's the difference between the secant line and
Tangent line touches the curve here at one point and goes in the direction of the curve. The secant line connects 2 points on the curve. The secant line slope is an average rate of change. Tangent line slope is an instantaneous rate of change. Great question. For the limit definition in red, same picture, but I label this point as C and this point as X, so that my 2 points here are f of x and f of c, and their difference is f of x minus f of c. All over x minus c gives me the difference quotient, the average rate of change, and we make it instantaneous by letting delta x go to 0. Notice that x does not go to 0. The width, x minus c, goes to 0.
handling f of c minus f of x over c minus f of x?
Yes, because that would be multiplying top and bottom by -1. And in some instance, if your point x were drawn over here, that would make sense. And this limit is limited from both sides, so some of your x's really are over here. Okay. That's our limit definition. We use the limit definition when we have to, basically, because evaluating that limit definition is a pain in the neck. And you remember doing some of those derivatives by hand. We call it finding the derivative by hand. Rather than use the limit definition, whenever we can, we would like to use our theorems to make our lives easier, and our theorems we're also called derivative rules. Let's see. Constant rule, what is it?
You're in the regular.
Good. And k can be a simple constant like 4, or a fancy constant like pi squared, or sine of square root of 3, or whatever. How about the sum rule? Oh, let's do linear function rule first. the derivative of linear function
Equals
the derivative of a straight line is its slope. And that makes sense, since the derivative is finding the slope of the curve. Oh, no. That's unfortunate. No. Some rule. The derivative of f plus g is difference rule. The derivative of f minus g exactly so. Constant multiple rule. The derivative of k times f of x is the same as but the product rule is where we started to have to be really careful. The derivative of f times g is
GF prime cos GF G.
exactly, and I usually write it the other way, but it doesn't matter which way I write it. The formula is symmetric because multiplication is, yeah, what is that? No. Commutative. There's no n in it. Commutative. Yes.
So we can write f g prime plus f prime g.
Sure. Now, are these two rules in conflict with each other? No. What happens if I apply the product rule to a constant multiplier? What happens? I get k f prime plus 0 because the derivative of the constant is 0. So the constant multiple rule is really just a special case in my product. Quotient rule. The derivative of f over g is
G times
exactly. And all of you have the order because you remember the song. We won't sing it at this time. And also, all of you understand that since g is not a common factor here, there's no canceling that you can automatically do. All right, well that left us with three specific types of functions. We've had power rule. The derivative of x to the n is equal to
x to the
yeah. And what types of exponents can we apply the power rule to at this time? Positive integers and negative integers and 0. In other words,
Not
like x to 0 is a constant.
right. Yeah. So therefore, since this applies to all negative integers, all positive integers, and 0, no, that's a little too far. All integers. Later on, we will extend this power rule to include other types of numbers, but so far we've only proved it for all integers. Okay. Power rule. Let's see here. We also had a square root rule. The derivative of the square root of x yep. And the derivative of the absolute value of x these derivative rules are going to be the majority of what you are going to be end up doing on the test. The question came up in the other class, do we need to know proofs? There are some proofs that you will need to know, and I'm going to go ahead and promise you that I will ask you to prove one of the following derivative rules. Either sum rule, constant multiple rule, square root rule, or difference rule. Yes?
We just worry about 4 proofs.
Yes. The power rule requires some algebra that I touched on, but you have not necessarily mastered in previous classes. And the others, I think, are too long for the test. Yep.
What about absolute value?
Absolute value of x, it's good to know, but I'm not going to ask that one. The absolute value of x, honestly, is easiest to see from a graph.
Yeah.
Because when I look at f of x equals the absolute value of x, it's really obvious that f prime is going to be -1 when x is less than 0, +1 when x is greater than 0, and now that I know about sharp corners, it doesn't exist if x equals 0. That's really clear. And so this function can be concisely written as x over the absolute value of x, and we're done. That's my best way to do that proof right there, to remember.
But you have to prove how it goes constant.
Well, right, so if I'm doing a formal proof, then I have to do all of that. But I don't find that valuable, is what I'm saying. Whereas here, these guys really are valuable to know how to use them. Good. Let's see. So we had limit definition. We had our various derivative rules. We also had our cited derivatives, way back up here, along with the types of non-differentiability, the 4 types of non-differentiability. Those will play a small role on tomorrow's test. And we've also had some familiar questions that you guys know about. For example, find the equation of the line tangent to y equals x squared minus 3 at x equals 1. Something like this. And so all of you are comfortable with doing this, but I want to remind you of the format because a couple of students, and I don't remember if it was in this class or the other class, a couple of students are getting confused about the difference between the derivative at x and the derivative at the point C at tangent C. And the easiest way to keep your head straight is to use the format here, slope and point. And the slope of the line tangent at x equals 1 is y prime of 1. It is not y prime of x. And the point is 1 comma y of 1. It is not x comma y of x. Does that make sense? And so in particular, we can immediately compute y prime of x to find y prime of 1. What is y prime of x here? And therefore, y prime of 1 is 2 times 1 is 2. That is the slope I will use.
So we don't have to use any.
Not unless I say so. Yeah. I'll come back to directions in just a minute. That's a good question. And what is y1 in this case?
Minus 2.
Minus 2. Exactly. So I immediately do y minus y1 equals slope of x minus x1. And what do I do to simplify it? Nothing. Exactly. We're done. Very good. Similar kind of question. Find points of horizontal tangents. If y equals, let's make it g of x equals x cubed minus 3x. Something like that. What is my concept that I need to express in my solution? Exactly so. Because my tangent line is horizontal, it has a slope of 0, and the slope of the tangent line is g prime. So this should really be the first thing that goes on my paper. And then we can fill in the details, because g prime of x is 3x squared minus 3. And now we can solve by factoring. And we're done. Yes, sir.
What if we don't settle in a few context of x equals to?
Then you get a big raspberry from me. Do it. The concept is horizontal tangent. So do that first. And just expressing the concept first helps so that you can fill in the details of it. Last thing right here is the bell rings. And that is, under what circumstances do you have to do what? If the directions say, use the limit definition, then you need to use the limit definition. Nothing else will do. If the directions say, use derivative rules one at a time, then you need to show, I should be able to look at your work and say, okay, that's constant multiple rule, that's sum rule, that's power rule. But unless I use that specific language, you are free to find the derivatives however you need to, including calculus. Like second calc dy dx, right? So you can use whatever you need to in order to find the derivative. I recommend for product and quotient rule that you set that up as a separate step to avoid dumb mistakes. Does that make sense? If you have product or quotient rules to do, I recommend writing that as a separate step so that you avoid algebraic errors. Yes?
And for the one at a time, we have to write which one we're using?
No, I'll be able to tell. Okay? Yes?
You have two related functions.
Right. And if I say use one or the other, you must. Otherwise, you can use either. All right. See you tomorrow.
Finally,